Hi, welcome back. So this is going to be the second video, and today we're going to talk about the types of groups we have. So let's get right into it. First up, we have, or groups, sets, my bad. So we have, the first set is the set of natural numbers. This is how this is the symbol for the set of natural numbers, and the definition is the natural numbers are the numbers that we use to count with. So 1, 2, 3, 4, 5, etc. Depending on some classes, 0 might be considered a natural number. Here we will say that 1 is the first natural number and 0 isn't a natural number. So yeah, so we have 1, 2, 3, 4, etc. and up to infinity. We have two operations that are noteworthy here. So the first is addition or plus, and the second one is multiplication or times. So these are the two operations. I'm pretty sure everybody at a high school level is familiar with both of these. So you have, like, for example, 1 plus 1 equals 2, or you have like 2 times 2 equals 4. And yeah, they are closed. The set of natural numbers is closed for addition and multiplication. What does this mean? It means that if we take any two numbers that are natural numbers and we either multiply them or add them together, we will get another natural number. Now, the second set we have is the set of integers. So, what are integers? Well, integers are all natural numbers, the neutral number 0, and the opposite of all natural numbers. So they're opposites. So we have -1, -2, etc. So we have the extra operation of subtraction here. So we have so we have to infinity, -2, -1, 0, 1, 2, and so on and so forth. So addition works the same way, except we need to have a new case here. So previously we knew how addition works, we just add the two numbers together. Now here we also have addition, we have subtraction, which is basically addition, but it works in a bit of a nuanced way, and we have still multiplication. So we have, for example, 2 minus 4 is the same as 2 plus the number, the number -4. So that's how it basically works. This is the modification we need to have to subtraction in order for it to have the same, in order for it to work. And addition and multiplication works in the same way as previously. The only, I guess, new thing is that if we multiply a negative and a positive number together, we're going to get a negative number. And if we multiply two negative numbers or two positive numbers, we get a positive number. Now, here another thing that you should know is that, the integers are also closed for all of these operations. So you can't really take any number, any integer, and subtract it with another integer and not get an integer. Okay, so this is the second set, so the set of integers. Now we have rational numbers. The notation is this Q with the extra line. What does it mean? Well, you can take any two integers and divide them. So we just add the opposite operation of multiplication. So here we had addition and multiplication. And we added another operation, which was subtraction, and that was the inverse operation of addition. Now we're going to add the inverse operation of multiplication. And how do we define rational numbers? Well, we define them as a quotient between two numbers, so P and Q, where P is a integer and Q, if we remember from our previous course, the logic symbol and, Q is an element of natural numbers, and their greatest common divisor is 1. What does it mean? What does this mean? This means that the fraction is reduced. Okay, so the common divisor between P and Q is equal to 1. In college, we would actually form them using equivalence classes, but here we will just use this extra condition so that it has to be a reduced fraction. Okay, so what does this basically mean? Well, we have another operation which is basically just division. So we have the same one, so addition. And how do we form how do we formulate addition of two rational numbers? Well, p and q, or let's say rather a and b, a divided by b plus c divided by d is equal to ad plus bc divided by bd. So that's how we would form addition for rational numbers. Next we have the division, or sorry, the subtraction. We would just add a negative sign here. We have multiplication, so we have AB times CD is equal to AC divided by BD. And then we also have the division, so AB divided by CD, or we can also write it as AB and CD like this. These two are equivalent because division and the fraction sign is just they're equivalent, they both mean division, equals AB times DC, and this is equal to ADBC. And the same thing goes here, ADBC. The way I remember this formula is that the outer one is the way I remember this formula is that the outer ones are multiplied and the inner ones are multiplied together, and the one on top stays on top. Okay, so AD divided by BC. And that's how we form rational numbers. Now, how do we form real numbers? And what even are basically rational numbers? Well, rational numbers are numbers that we can write in this form. We also have a decimal form. And how do we convert to a decimal form? Well, you basically just divide these two numbers and you're gonna get the decimal form. And what types of numbers can we even write here? Well, we can write any any number that ends, so that you have, for example, 7.1234 and then infinite zeros, and any numbers that have a repeating infinite amount of digits. So for example, if you have 3.333 etc. at infinity, then that would be also an example that's valid. So what's the common thing between them? Well, you can write them as a reduced fraction, and you can also write them their denominator as a power of 10. Okay, so if a number can be written in a reduced fraction, it can usually be written in a power of 10. Okay. Okay, so yeah, moving on, we have the so-called real numbers, and this is the notation for them. Well, what numbers do we not cover? Well, we don't cover infinite non-repeating numbers. So, for example, pi or e or anything like that, that's square root of 2. All of these are irrational because you cannot write just a repeating amount of digits. So, for example, here you say 7.125, 125, etc. You would just write this instead. With reals, for example, for pi, you do not reach the end of this, and it's not going to be a repeating sequence. It's going to be a randomized sequence, and, well, not really randomized, but it's going to be a sequence and you'll never reach the end of it. For reals, so these are so-called irrational numbers. In some cases, some people do have like an I notation like this for irrational numbers, but you do not do this in high school or college generally. If you want to have the set of irrational numbers, you write the reals without the rationals. Okay? Now, how do we define real numbers? Well, basically just any number is basically a real number. Okay, so we're going to define them as just, and that's the way we're going to define them. Okay, so and all the rational numbers, okay, plus all infinite non-repeating decimal numbers. Okay, so infinite non-repeating decimal numbers. Okay, numbers. We don't have a very formal notation like we do with Q here, because generally speaking in college we would define them using Dedekind cuts or for Cauchy sequences, but yeah, here we just write it with our words. So these are the reals, okay? And the operations that we have here are basically just, we have the addition of square roots, for example, or cubic roots, etc., that we didn't have previously. Now, how do we even prove these numbers exist? Generally speaking, what we do is we prove that the square root of 2 is irrational. So we're gonna just write proof square root of 2 is irrational. And we do that using the proof by contradiction, which means we're going to assume it's true and then prove that this leads to a absurdity or a contradiction. So let's assume that the square root of 2 is rational, okay? Irrational by definition means non-rational. And technically speaking, if we're being completely accurate with semantics, this isn't really proof by contradiction, but it's just proof of negation, like for the logical operation not, because irrational by definition means not rational. But this is this is nitpicking a lot. So let's just say it's contradiction. Assume that the square root of 2 is rational. This means that the square root of 2 can be written in a reduced fraction, pq, and it follows that the greatest common divisor between p and q is 1. What does this mean? Well, we can't reduce the fraction further. For example, 3 and 2, we can't reduce this further, okay? Now, let's square both sides. So we have 2 equals p squared divided by q squared. And we get that q squared equals 2 times q squared equals p squared. So like this. And this implies that p squared is actually a even number, okay? Is even, okay? So, because it's 2 times some number, which means that we can write that p is 2 times some even number, okay? Why do we know it's even? Well, because it's multiplied by 2 here. This means it's even. And if it's an even number, it can be 2 times something, okay? So we write 2 times q squared equals, instead of p, we write 2 times p0, okay? And this leads us to have 2 times q squared is equal to 4 times p0 squared. And then we can divide by 2. And we get that q squared is equal to 2 times p0 squared. Okay, what next? Well, this would imply that q is also an even number. So it's 2 times q0. Because we have that q is 2 times p0, okay? Squared. And what does this mean? Well, it means that p is even and q is even. Well, if both of them are even, then their greatest common divisor can't be 1, because the greatest common divisor of any 2 even numbers is 2. At least, like they're for sure at least divided by 2. It can't be 1. So we reached a contradiction. And this means that the square root of 2 cannot be rational. So this is basically how you would prove it. And fun fact, when in ancient Greece, when Pythagora basically had a student that showed this proof to him, Pythagoras ordered his guards to basically kill him because he couldn't believe that such an ugly number existed. So that's a bit of a history lesson. And the last group of numbers that we're going to very briefly cover are complex numbers. We're just going to mention them. We're not going to mention much more than this. Complex numbers are composed of two parts, the real part, A, and the imaginary part, so BI. And this is the imaginary unit. Imaginary unit. And what it means that I square equals -1, okay? This is all we're going to talk about because we're going to cover them separately and they're kind of unique in this matter, so yeah. We're just going to end at the reals right now. And that was basically the sets that we have. So the set of natural numbers that we said are the numbers that we used to count with. The set of integers that are basically the numbers we use to just have addition, subtraction, multiplication. It also means that basically they are the opposites of natural numbers, and also we have the neutral element 0. We have rational numbers, which is defined as a quotient between an integer and a natural number, and the reason we do that is because if q is a natural number, we don't have 0 here. We can still form every single rational number because we can get the negative sign here from p, and the only difference is this way we can also say like q is a integer and q isn't 0, but by saying q is a natural number we avoid this condition. So that's why we write that q is just a natural number. And then we also formed the real numbers, which are just infinite non-repeating decimal numbers, okay? So the ones that can be written in a form of a reduced fraction. And that basically encapsulates all of the sets that we basically need to know right now in order to start talking about basically equations and some properties of numbers and how we're going to multiply them, and we have some rules that we're going to follow. And yeah, for this video, this is going to be all. I hope you enjoyed it, and I will see you in the next one. Goodbye.